In the previous video, we were trying to work out the volume underneath this surface within this region, and in order to do that, we would convert this dA. We would convert this dA into this thing here. So in order for us to use polar coordinates, we have to, for some reason, stick this r in here. If you work in Cartesian form, dA can simply become this. So in this video, we're going to try and understand where this r comes from. So the idea here is that if you're trying to work out the area within this region, you would cut it up into equal delta angle, delta theta. So cut this up into equal angles. So it's like this, and then you've got one radius here, you've got another radius here, and then you've got the outer radius here, and then you've got one radius here, and the outer radius here. So the idea is to sum up each individual component. So here, let's just say you're currently here. So this area here, hang on, let me think. So this area here, you somehow work out this area, and then once you've got the area, you would jump to the height of the surface. So you jump to the height of the surface. So once you've got the area, you times by the height, it would give you a volume, and then you would sum up all the volumes. You would sum up all the volumes. So let's try and understand what's going on here. Hang on. So in Cartesian form, dA is this thing here, and it makes perfect sense because let's say you're currently standing here. No matter where you are on the Cartesian plane, if you are standing here, currently the area is 0 because you're standing at a point. A point is not an area. If you give me a delta y and a delta x, then the change in the area traveled from an area of 0 to an area here. Well, this area here is simply dx, delta x times delta y. If you're standing here, the change in the area is simply this times this. But then if you're working in polar form, it's not simply it's not a simple case of getting the change in the radius times with the change in the angle, because let's say this is the change in the angle here, d theta. This is a change in the radius. So this is also dr. This is also dr. This is also d theta. This here is also d theta. But let's say you're standing here. Currently the area is 0 because you're standing at a point. Well, if you give me a change in an angle and a change in the radius, then this times this will give me some sort of number. But let's say you're standing here. If you're standing here, then you can see that this area is not the same as this area. So we can't simply use dA times dA is not the same. It's not equal to dr times d theta. There has to be some sort of weird relationship going on. As it turns out, you need to stick an r in here. But let's try and understand why. So we need a fair way of getting dA. We need a fair way of getting dA. This simply is not good enough. In order for us to obtain this dA thing, we need to work out this area. So let's just say, hang on. The idea, a fair way of getting this dA is to do this. Hang on. Let's say you've got a big radius, big R, and a small radius, small r. So from here to here is small r. So we need a way of working out this area. So the idea here, our next aim is to work out dA. So it will be pi big R squared, take away pi small r squared. So that will then give us this donut thing, and then you would cut up into let's just imagine we're working in degrees, 360 equal pieces, and then you get theta pieces. That will then give you this piece here. That's the idea behind it. So let's put it to practice. So let's say this is this here is currently r, this length is r, and we need to somehow work out this area. Let's just say the area here is this thing here. Let's just imagine that this area here is this area here. So we currently have r, so that's this r here, which is this r here. Well, we need to get the outer radius. So you would get r, and then plus, remember this distance here is delta r. So you need to add half of delta r to get the outer radius. So this big radius here, is this thing here. It would simply be r, which is this thing here, plus half of delta r. That's this distance here. So this thing here would be like the big radius, and then you pi r square it. That would then give you the big circle. That would then give you the big circle. That would then give you the area of the big circle, and then you would take away what's the small radius? Well, the small radius would be you getting r, which is this radius here, and then take away half of delta r. So you take away this half delta r here. So that would then give you this radius here. That would then give you this radius here. So we are simply working out this area here. So get the big radius, pi r square it. That will give you the big circle, and then take away the small circle. Hang on, take away the small circle. That would then give you this thing here, and then you divide it by 2 pi because we work in radians, and then you times the delta angle here. The delta angle, that will then give you this intended area here. That will then give us this area here. Well, think about it. The whole area is given by this thing here. So this area is given by this. So now if you tidy this up, the pi's will cancel each other out, and then this gets multiplied to the top. You can factor it out. That will then give you this. So this whole thing here simplifies to this. So now let's use algebra. So if you multiply this out, it will then give you this thing here. If you multiply this thing out, it will then give you this thing here, and then tidy up, it will then give you this thing here. It will then give so that area there. I'm asking you to imagine the area as that. Why that? I'm asking you to imagine that this area here is given by this. I'm asking you to imagine that. But the thing is, imagine you're standing here at the moment. You're standing here at the moment. So because you're standing at a single point, the area will be nothing. It will have an area of nothing. But only when you give me a delta angle and a delta radius, then will I register some sort of area. So to travel from an area of 0 to an area of something, let's just imagine this area is, I don't know, 7, and it has an area of 7. So you can see that from a single point, only when you give me a delta r and a delta angle will I see a change in the area. So here I'm just using this bit here to I'm just asking you to imagine the area as this, but really for us to interpret it, it has to be dA, because I've gone from an area of 0 to an area of something. Only when you give me an area, only when you give me a delta angle and a delta radius will I see this change in the area. Well, this change in the area is really dA. So I've gone from A to dA, and I hope you can accept that. From a single point, you standing from a single point, you have an area of nothing. Only when you give me this and this will I register a change in the delta area. Well, the delta area is you getting some sort of change in the angle, change in the radius, and combine that with your current radius. Then it will give me a fair way of obtaining this dA, this delta A. So you need to take the radius into account. So even if you're standing here, let's say you're standing here, you've got to take the radius into account. Take this radius into account, and then combine it with the delta r and the delta theta. Then it will give you a fair way of measuring this change in the area. So even if you're standing here, well, if you're standing here, take into account your current radius, this r here, and then combine it with delta angle and a delta r. Then it will give you a fair measure of this angle here. Of this area here. I hope you can accept that. So hang on. So to convert from delta A into polar form, you need to stick this r here. Without this r, there's no way of getting a fair area. You need that r. So let's if you're still having trouble understanding this, let's jump back to Riemann's sum. So this is a crude way of explaining. There's a lot going on here. I've oversimplified this whole thing here in the hope that I could explain it to you. So this is not technically correct. It's not technically correct, but I'm just simplifying it to give you an understanding of what's going on. So let's just imagine we're trying to integrate it over a region of pi of 90 degrees, pi over 2, cut up into 3 equal pieces. So your delta angle is this angle here, 3 pieces. Okay, and remember, this is not technically correct, so bear with me for the time being. And the radius, this distance here is 4. We'll cut it up into 4 equal pieces. So delta r is really this length here, which in our case is 4 divided by 4 is 1. So we would set up this counting mechanism. All this is a counting mechanism. So you've got a thing nested inside another thing. So it's just a counting mechanism. So for the first angle of 1, so this is an angle of 1, and an angle of 2, and an angle of 3. For the first one, angle of 1, this thing here loops around 4 times, from 1 to 4. So when an angle of 1, loop inside here. So r counts from 1 to 4. So the first one is this. That's r equals 1. The second one's this, and the third one's this. The fourth one is this. Now all this is done. Go back to the outer integral, and then consider theta equals 2. So that's this angle here, and then loop around again 4 times. 1, 2, 3, 4, and don't forget, each time you loop around, this thing here jumps to the surface. This thing here jumps to the surface. So you're working out the area. So this thing here is like the area, a fair way of working out the area, and then you times the height of the surface. Then that will give you some sort of volume in 3D space, and so that would give you some sort of volume in 3D space. And then you jump to the second one. So work out this area here, and then times it by the height of the surface. That will give you another volume. So you're summing up all the volumes, and then so this is what's happening here, is that this thing counts. So when theta equals 2, this thing loops around 4 times. So theta equals 2 is here, which was where we were earlier, and then loop around 4 times. 1, 2, 3, 4. When all that's done, then go back to the outer integral, increment it by 1. So theta would be 3. So theta equals 3 is here, and then start looping around 4 times again. 1, 2, 3, 4. So eventually it will sum up all our pieces, and then it will give us our region. So this is just a counting mechanism. I hope you can follow that. Okay, but the important thing is, you need to stick this r in here, and it's the only fair way of working out the change in the area. Without this r, it wouldn't be fair. Okay.